so much, Yvonne. And Carly, David, and Bill Botke, if you wouldn't mind coming up here for the first panel session. So I'd like to add my welcome to that of Carol's, our administrators, and Yvonne's. This is something that we look forward to every year. It's just so exciting to be able to talk with all of you, share what we do in Survey, see things that the other things that the vast community that we work with does, welcome our international partners. It's really a privilege to host this meeting. What I have a privilege of doing right now is introducing something very special that we were asked to do a little over 6 months ago. Yvonne and I and Jim Green, who was then the head of Planetary Sciences, met with 3 associate administrators right around the beginning of December, including Thomas Zurbuchen, Bill Gerstenmaier, and Steve Jerzyk. And when we met with Thomas Zurbuchen, we got into quite an animated discussion about lunar science. And he, for those who don't know, is the head of NASA's science enterprise and the billions of dollars that are spent every year doing the wonderful things that NASA is able to do. And so what Thomas asked us, asked Yvonne and me, is what is the most compelling science that is going on now at the moon? And what kind of vision do you have for where it's going? He didn't want to see the ordinary stuff. He wanted to see the stuff that packed a punch. And he asked for a white paper. He asked Survey to lead this. We, of course, took it as a privilege to do this. And so we came back and we asked our PI teams to do this. And so Carly was the first call that I made, and Carly grabbed onto this, and the result is what you're about to hear and about to see in the white papers that Yvonne mentioned are available. So what I want to say is what this session is about is seeking feedback and having a dialogue with the community. Carly is going to say it even better than that, I'm sure. But I want to give a little context as well. This upcoming year is a very important year for us. You've heard from the administration, we are going, and I'm not going to say going back to the moon, I'm going to say going forward to the moon. This was Carly's insistence yesterday, and I love it. You know, we're not looking back, we're looking forward, and we're engaging all of the young people that I see in this audience and so many others around the world to do this marvelous task. And so I think that as we hear these words, let's think about the 50th anniversary of Apollo 11 coming up. Let's think about all of the opportunities that each of us is going to have in the coming year to engage with this community and to share the exciting science that we do, that you do individually, that the community does, and to engage the public. We know how important this is. We know how cool the moon is and how exciting it is, but it's our job to share that enthusiasm with the public. And I think that I heard a really great perspective yesterday from one of our PIs who said, how would you represent this transformative lunar science that you're about to hear to your grandkids, to your kids, to your grandkids? And so I think that's an important perspective. So I want to close by thanking Carly, Robin Canup, who was one of the principal authors, Jim Head, who's in China, and I don't know if we have him online, but I think Carly is going to represent his work, and then Apollo 15 astronaut Dave Scott. Thank you very much.
Well, it's a pleasure to be here. I forget, this is my clicker here, right? Okay. Transformative lunar science. the structure that we have here is, first I'll give an overall hand to channel him. This will be followed by a focus on different parts of lunar science and exploration, starting with the present and what we see from the position of where we are right now in the given position of the Earth and the Moon. And we'll transition from that into some of the very beginnings of the Earth-Moon system, and then end with the record of that the Moon provides. Giving an overview, these images should be familiar to all of you. On the left is what you see with binoculars or a telescope even before the space age began. So this is familiar to everyone on planet Earth. But then as the space age began in the late 60s, that the Earth and the Moon became a completely different perspective. And we recognize that our neighbor right outside our window every evening and sometimes during the day is right accessible to us. In the middle is one of the first really lovely images taken by Apollo 8 as it swung around the moon, not landing, but first time to swing around the moon and seeing the character of the Earth as viewed from the moon. And of course, there's the famous Apollo 17 image of the blue marble that set everybody's perspective of our planet from the view of space. One of my favorites, and I'll return to this in a moment, is the image in the lower right that the Galileo spacecraft obtained as it came by the Earth-Moon system for gravity assist to go on its way to Jupiter, and the spacecraft turned back and looked at the Earth-Moon system as it was quite far away, and obtained this family portrait. And it's rare to have such a wonderful snippet of the Earth and Moon together in its natural state. Now, this is sort of history, but some of you may not remember it. There were a large number of missions before the first Apollo 11 mission to the moon, which we're going to be celebrating the 50th anniversary. 21 robotic missions. Some of them were not successful. It's important to remember. But each one of them provided information that allowed us to move forward and to explore the moon with not only robotic, but eventually human on the surface as well. And then, of course, we all hold dear to our hearts a series of Apollo missions that were so productive, so rich with science that is still continuing to date because we have lunar samples from each one of these. And with the technology that continues to improve in our laboratories, the capabilities and new insights and new discoveries continue every year, essentially. And part of the understanding is recognizing the place that the moon the insight that the moon provides us to understanding the overall character of the terrestrial planets. The moon is strongly established as the cornerstone for solar system science. Of course, after Apollo now, because it starts with some of the highly the L-Cross impact event that identified the volatiles at the poles, and a whole series and diversity of instruments on this spacecraft moon. Followed by several important additional missions, LADEE, understanding the atmospheric and dust environment of the moon, and of course GRAIL, the Gravity Recover and Interior Laboratory, which has completely changed our understanding of the structure of the outer portion of the moon. These have been landmark exploration missions that we continue to use in our analyses and integration of our analyses today. Now, there is, as was mentioned, the national commitment for boots on the moon and then on to Mars. I think everyone in this room strongly supports that, and I'm delighted with that myself. But there's a lot of additional properties that are tied to that. Obviously, there's infrastructure that needs to be done to have a serious exploration program. The Gateway is one step in that is on the books. Commercial involvement and capabilities and opportunities that will be blooming in the years ahead. And of course, feed forward to Mars. And through all of this is bringing the next generation of scientists and engineers into the forum and active members of our lunar and planetary community. With that as an introduction, in fact, we will now start the discussion that really are exemplified in this document that you can have a copy of, and it's also available online, of the Transformative Lunar Science. What I'd like all of you to be thinking as we go through these presentations, to be not only thinking, oh yes, I know that, but to be thinking, okay, what are some additional activities that are transformative that we ought to be making sure are part of our lexicon, part of our discussion in the years ahead. So after we go through this sequence with my colleagues here, we definitely want to have a dialogue with the rest of you about transformative lunar science. So let me start with the present. And I'll start with my favorite family portrait of the Earth-Moon system. And for those of you who are not terribly familiar with this image, look closely at the moon. And as you probably can recognize, with this orientation, the moon can either be on the opposite side of the Earth or it can be on this side of the Earth in terms of how this image was taken. And I hope more than 50% of you can recognize which side of the moon we're looking at. It's, in fact, the lunar far side. It doesn't have the markings that you see every day when you look up from the Earth, because, of course, the near side is the only side you can see from the Earth. This is the lunar far side, and that little smudge down at the bottom is the South Pole Aitken Basin that has a low albedo. It's an enormous basin. It's an unsampled, unexplored part of the moon, the largest, deepest, oldest basin on the moon. You can't really tell from this image, which is a lovely albedo image that we have now of the moon. But if you look at the topography, the character of the basin, the scope of the basin is obvious. And it's one of the major events, the oldest event, the biggest event that we have recorded on the moon. And it's on the unexplored far side of the moon. Okay, another unexplored area, of course, are the polars. This is another lovely image taken by LRO, passing over the poles and looking at the Earth. And as you all know, the poles have deep shadows, very deep shadows, where sunlight never reaches. And these areas, the permanently shadowed areas and areas associated with them, are areas of very active research. This is a wonderful image, product of the LRO, showing where some of these polar, deep, cold, dark areas at the poles are that we believe are traps for many of the volatiles, many lunar volatiles. The present Earth-Moon system is really important because the moon documents the environment that we on planet Earth share at 1 AU. With our atmosphere, we cannot record many of the events. We can't record the kind of small impacts that LRO has now been documenting through the decade that it has been looking at the surface of the moon. Last I heard, there's about 300 impacts that have been discovered. images like this where a before and after, I'm sure the number is higher. Ask Noah, and he, I'm sure, can tell you what the actual number is. So this is something that we can't really do on the Earth, but we have access to on the Moon with our ongoing lunar research. The present Moon is also a wonderful example of the space environment. And for those of you who are interested in geology and chemistry, space itself is not empty. Any particle or mineral atmospheric scientists and exoscientists will tell you that there's plasma everywhere, and particularly the plasma from the sun, the solar wind, that's primarily hydrogen, but lots of additional ions and elements. The environment of exposure to the surface includes minor amounts of dust, charged particles, exosphere, which is what we call the lunar atmosphere, of a wide variety. Here's an example that in the sodium line, you can see that even sodium atoms can be identified in the exosphere of the Moon. It looks dense, doesn't it? But it's really thin. But it's measurable, and with the appropriate detectors, you can capture examples like this. And of course, one of my favorite areas are some of these unusual magnetic anomalies that occur on the surface of the Moon, which we're still trying to understand how this localized magnetic field affects all the particle interactions that occur on the surface. There's these beautiful what we call swirl features that we have yet to understand. There'll be a session during the forum today focusing on them, and stay tuned for continued research in that area. What I want to spend the rest of the time I have is on the water cycle of the Moon. This is something new that really is only in the last 10 years that we began to recognize. It consists of polar, interior, and surface water, or hydration, or OH, using different terms depending on the particular scientist and their interest. The first that we recognized was in the polar areas, and this is some of the neutron spectrometer data acquired almost 17 years ago, showing that at the poles, in these permanently shadowed, in these very cold regions, there's an excess of hydrogen. And that's predicted to have been the accumulation over periods of time in these cold traps. Of course, then, less than a decade ago, we had the LCROSS mission, which was targeted for one of these areas that were had high potential for collecting some of these volatiles, and the series of experiments showing what was excavated by that targeted impact event was indeed extremely volatile rich. Not just hydrated materials, but a whole range of volatiles were associated with it. A really dramatic example of the kind of treasures that are still hidden on the Moon. Going down to the interior of the Moon in terms of the hydration state, this is not an image of the Moon. This is an image from Mauna Kea looking over at the Kilauea current eruption. And you can see it's in the evening, you can see some stars in the background. But the reason I'm using this image is to remind you that when we have the extensive volcanism, large volcanic eruptions, associated with that is also gases. And that's true, we believe, geologists believe, for virtually almost all the massive volcanic eruptions that we have in the solar system. Well, on the Moon, we know there are these enormous lava flows and locations that occurred 3.5 billion years ago, but they're massive, they're extensive, they're what cover the entire, all the low albedo, these dark areas, these relatively smooth areas, these maria, are essentially basaltic lavas that were extruded in the 3 to 3.5 billion year time frame. So with that, of course, going back to the volatile issue, to have this amount of lavas extruded in a relatively short period of time must have had an extensive amount of volatiles released at the same time. There's a lovely analyses that were done a year ago, less than a year ago, by associates with Survey, that calculated that the amount of volatiles would give a transient but substantial atmosphere to the moon, at least as dense as the current atmosphere on Mars. Of course, we have samples, so we can look at the samples to examine the amount of volatiles that these volcanic materials incorporated. And that, again, has been a very important analysis just in the last decade to identify that with the current technology that we have in our laboratories, that the ability to detect and precisely measure the amount of volatiles in, the example that I'm showing here is the volcanic glasses that are the most direct samples from the lunar mantle that we have in our sample collection. And by measuring the amount of hydrated materials in these samples and a suite of samples, allows us to not only measure the amount, but measure the isotopic composition, which is the figure that you see here that's summarized by Howry et al., and compare these isotopic relationships with other solar system materials. So this allows us to place the character and evolution of water in the Earth-Moon system in context with the rest of the solar system as well. So that's the interior, and then the third component is on the surface. Less than a decade ago, much to our surprise, we recognized with spectroscopy that the surface of the moon has a hydration feature at 3 microns. And a little sort of side story, when we first saw this feature in the M-cube data, we said, that's wrong. You know, we need to recalibrate our data. You know, it's got to be, we took it with us. So we spent months calibrating our data, tried to get rid of this. We could not get rid of this feature. So fortunately, we had other people on our team, one of whom, Roger Clark, who was on the Cassini mission. And when the Cassini spectrometer flew by the Earth-Moon system on its way to Saturn, it took some data of the moon, and it had a spectrometer that covered the 3 micron area, and lo and behold, in that data, there's a clear 3 micron feature. I said, well, okay, maybe we both were contaminated. Jessica Sunshine was on the Deep Impact experiment, which had done its business designed specifically to look for water and volatiles on a comet. And when it came by the Earth-Moon system, it turned its instruments on and measured the surface. And lo and behold, they saw the 3 micron feature. Now, we know that was not a calibration issue. So the 3 independent measurements of 3 independent spacecraft, independent measurements, all found the same thing. We were forced to recognize the surface of the moon has a hydrated component. And that's the third component in our water cycle. So one of the activities and really big questions and transformative issues that we need to be addressing in the years ahead is how these 3 components of the water cycle are related or interrelated. I don't have the answer for that. Hopefully we'll have more as we progress forward with new measurements and new instrumentation. And of course, this is really new science. This is just within the last decade that we even knew about this as an important science component. Okay, so to understand this water cycle, there are several things we need to do. I've just listed a summary here. We need to identify the origin of the water at 1 AU, and I say 1 AU because it's the Earth-Moon system, and part of the issues that you'll see in the discussion by Bill is we need to understand the Earth and the Moon and how they're related to each other, in particular how their hydrated materials are related to each other. We want to document the mobility of the water or the volatiles on the moon. How do they move around? How do they move around by day? Are there any long-term effects, short-term effects? These we have only hints of. We don't have direct data for yet. And we want to measure the magnitude of these resources. We want to know if any of these resources are renewable. And all of these require additional detailed analyses in the years ahead. And with that, I think I'm done giving you an introduction on the water cycle, and it's supposed to move ahead. Yes, okay. Well, that gives you an overview of the present. I will turn it over to Bill Bakke to give you a transformative science at the very beginning.
Great. Thank you very much, Carly. Just for the people in the video room, I have a few animations, which I think have to be started by hand, but I don't think I can do them with the clicker. So I may actually ask the people in the back room to start animations when it comes to that. Okay. So thank you very much. I'm replacing Robin Canup's version of the talk. I will try to be as articulate as Robin, but I'll fail, but I'll do the best I can. Okay. So there are many moons in our solar system, but our moon holds a special place because it potentially can tell us about the origin of the solar system, but also the origin of the Earth-Moon system, and the Earth is our home, right? From the oldest samples we have from the moon, we've been able to derive a potential estimate for when the moon formed. And we think the moon formed about 60 million years to about 100 million years after first solids condensed out of the solar nebula. And that puts it at a really interesting time because we believe that's the time of planet formation, right? One of the interesting things about the moon is that because it's so ancient, it tells us about the initial state of the solar system, but how planet formation may have worked. And that's one of the reasons it's such an interesting object to understand. So the way we think planet formation may have worked, and there's lots of discussion on this, and this is an ongoing conversation, but at some level, the zeroth order, it's a little bit like this. You can imagine solids forming out of the solar nebula. They begin to form small little planetesimals. Those planetesimals begin to grow larger and take on the form of small little protoplanets or mini planets. There may have been tens to hundreds of these objects. Eventually, they began to collide with one another and grow into larger objects, and eventually they took on the system of the 4 terrestrial planets we have today. But the model suggests that towards the end of that formation process, some very, very large collisions were taking place, probably with almost every terrestrial planet. And one of the last biggest collisions to take place was one that hit the Earth and potentially created our moon. So that means collisions are a fundamental geologic process in terms of understanding planet formation. So if we want to understand how our system of planets formed, we need to understand giant impacts. If we want to understand how exoplanets formed, we need to understand giant impacts. It's a process that happens across our solar system, across the galaxy, across the universe. It's an important thing to try to understand. Okay. So the idea that our moon formed from a giant impact probably goes all the way back to the early days of the Apollo era, where people were suggesting it. But our ability to be able to model it in kind of a sophisticated numerical way has probably arose maybe 20 years after that time. And at that point, we had models that could account for the temperatures, for the pressures, for the equations of state, everything that would go into these simulations. And they suggested a certain avenue to try to explain how to get the Earth-Moon system. Okay? So in these codes, what they would do is they would take different projectile sizes with given masses, different velocities. They would try different angle of impacts on the proto-Earth, and then they would try to see what would emerge out of that. And the main constraints they used at that time were the mass of the Earth, the mass of the moon, the initial rotation state of the Earth, how fast it was spinning, and then also issues like why does the moon not seem to have a large iron core? These were all issues that fed into this. And so these models had some success. Okay, and so I'm going to be showing you an animation in just a second here, if I can get it to run. And so what you're going to be looking at is a Mars-sized object. Oops, there it goes. Okay, you're looking at a Mars-sized object hitting roughly an Earth-sized object. It's hitting at an angle. Okay, so what that allows you to create a disk of material that ends up being in orbit around the proto-Earth. The colors here represent temperature. So green represents molten rock. Red actually represents vaporized rock. Okay, so it's a little bit slow. No, it's actually much better over here. Okay, so the disk is going around. You're seeing some material reaccrete back with the Earth. But in this particular simulation, you're actually getting enough mass into what we call the proto-lunar disk that eventually, if you follow this long enough in different codes, you would see a mooniform with most of the properties that we have today. And because these kinds of impacts match the angular momentum of the Earth-Moon system very well, and they explained other constraints, we thought to some high degree of accuracy that we had solved the problem. And I say we, the collective we of the field. So the consensus was, well, we understand the moon-forming event, we're done, right? So this is where we stood as about 20 years ago. But over the last decade or so, some new measurements coming from the geochemistry field and others have suggested that we may be missing something fundamental, that there's something very disturbing about some of the measurements we're getting, and that maybe these kinds of impacts that seem so straightforward are not the solution on how we get the moon. Okay, so let me highlight some of the problems that we may have. Okay, so I can show this a little bit on the figure on the left. Okay, so this shows sort of the two objects prior to the collision. And all the colored bits, you see the yellow and the red and the rest, that's the material that ends up going on to form the moon. Okay? And what you'll notice from the picture, that most of our moon seems to come from the impactor. So whatever properties the impactors would have, you might expect the moon to have a very similar kind of property. Okay? It doesn't actually look very much like the Earth. Okay? So, but then this raises the problem, right? So now we have to understand the composition of the moon to see if this actually makes sense. And so the question is, did the impactor that hit the Earth look like the Earth, or was it have a very different composition from the Earth? So one way we can sort of explore this in an interesting way is to look at samples and try to explore planetary compositions using the ratio of isotopes of different elements. And one way this has been done in the past is to use oxygen. Okay, so we're looking at the plot on the right. So oxygen has 8 protons and 8 neutrons. And we call that 16 oxygen. But some oxygen has an extra neutron or maybe 2 extra neutrons. And when you take ratios of those isotopes to oxygen 16, you can get interesting relationships. And so we can use this to look at, let's say, water on the Earth. We can look at water vapor in the clouds. And what we do is you get a very nice relationship, even though the measurements are individually a little bit different. The trend line all suggests that possibly we're from the same body. Now, if we go look at Martian meteorites and we do the same experiments, what we find is that Mars has also as a trend line, but the trend line is very different than that of the Earth. Okay? It's very easy to see Mars is distinct from that of the Earth. So if the projectile that hit us, which we think was Mars-like, which think was Mars-sized, had the same composition as Mars and the same isotopic properties, one would expect the moon to look like Mars, according to simulations, but it doesn't. Okay? The moon actually looks remarkably similar to that of the Earth from an isotopic perspective from these ratios. Now, this has been known for decades, but at some level, the accuracy of these measurements was, let's say, was imprecise enough that there was some room for margin to say there had to be some difference between the Earth and the impactor that hit the Earth. But over the last decades, these measurements have gotten increasingly precise. To now, effectively, you could almost argue that the Earth and Moon are almost identical in terms of their oxygen isotopes. And this creates a real fundamental problem in trying to understand how we can explain our Moon. So let's go to the next slide. Okay, so over, let's say, about the last 10 years or so, there's been several potential explanations for this. And I could actually think of some more off the top of my head, but we'll go with these 3 for the moment. So the first suggestion is to suggest that right after the moon-forming event, you create a proto-lunar disk with essentially a large vaporized component. And that vaporized component mixes with the vaporized component of the Earth, and that mixing is so thorough that effectively what you get in the end from the moon looks very similar to that of the proto-Earth. That's a process called equilibration. It was pioneered by Kaveh Pavelin, and it's an interesting possibility. Okay? The second possibility has to do with, can we change the nature of the moon-forming event to get maybe a solution more satisfying? And there's sort of 2 different avenues this could go down. So one avenue, suggested by Matja Chuk and Sarah Stewart, is that you had an extremely fastly rotating Earth. So it was rotating maybe once every 2 hours or so. And then it was hit at a very high velocity by a somewhat smaller projectile, smaller than Mars. And that collision was so energetic that it created a proto-lunar disk with mostly Earth material. And so the reason the moon looks like the Earth is that essentially it comes from the Earth. Okay? The other possibility was suggested recently by Robin Canup. She suggested what would happen if you had two half-Earths slam into one another. And if the collision characteristics were correct, you could have such profound mixing between those two half-Earths that what you get in the end would be well mixed, but also the protolunar disk would be well mixed. And so the disk that makes the moon and the Earth would have very similar properties. So all these are different scenarios, and again, there's some interesting ones we can go as well. But ultimately, how do we solve this problem? How do we deal with where we were and then how these models, which ones do we know were right? Okay. Well, to understand that, we have to ultimately get more data. That's the only solution that we're really going to be able to do to solve this. And so there's some different questions we can ask on the kinds of data that we want that may actually go after this problem. Okay, and it falls down to three main questions that I'm going to talk about here. Okay, so first of all, can we say something about the nature of the lunar interior? And at the moment, all the samples we've received from the moon, we think, for the most part, have come from the surface, right? They've come from the top few kilometers. Very few samples act as probes into the deeper interior, with some few exceptions. And we also do not think we have a sample of the lunar mantle. So how do we get the sample of the lunar mantle? Well, one possible way to do that is to take advantage of what nature gives us. On the far side of the moon, Carly talked about the gigantic basin, South Pole Lake Basin. It may have hit and produced such a deep hole that we may have excavated portions of the lunar mantle. So if we go to the far side and we look either inside the basin or inside the ejecta or inside other basins that may be existing in SPA, from all of that we may be able to find a remnant of the lunar mantle, and that may tell us a lot about what the interior could be like. The second possibility, and this is actually, and they're not mutually exclusive, we may need both, is to think about pyroclastic deposits. On the moon, brought back by Jack Schmidt, who's in the audience somewhere over there, he brought back pyroclastic deposits from Apollo 17. And these little glassy beads, we believe, formed in fire fouling events, but ultimately they're derived from magmas, which may actually be sourced in the mantle. Okay? So by understanding the nature of these pyroclastic deposits, we may get insights into what the mantle was like. But there are many different pyroclastic deposits around the moon. We've only sampled a tiny fraction of them, and it could be by sampling many more, we'll learn much more about what the mantle could be like. Okay, the second issue has to do with sort of the nature of the interior of the moon. Is it homogeneous or is it heterogeneous? All right, and there's different ways to think about this. Okay, so some models suggest that right after the moon forming event took place, we had a pronounced magma ocean, but that magma ocean was so deep, it actually went all the way to the deepest inside of the moon. The whole moon was molten. And if that were the case, one could imagine a much more homogeneous moon growing out of that after it formed a core. The second possibility is that the first part of the moon to form was the material that came right out of the giant impact. It actually didn't last very long in the protolunar disk. That created an interior component, and then on top of that material it created on top, and only the material on top went through a magma ocean phase. So in that case, the magma ocean may have only gone a few hundred kilometers down, and the rest of the material may not have melted. That suggests that if we go to the deepest interior of the moon, we may actually have a very different isotopic component than we have on the surface, possibly. Okay? So how do we get at these kind of two fundamental differences? One possible way to attack this is through a global seismic network. We put seismometers across the moon, we have active experiments, and we probe what the deep interior of the moon might be like. Okay? We can also think about combining that with heat flow sensors that will also be a global network, which we put across the moon, and then we try to understand how does the heat flow in different regions of the moon change with time. Those two combined may actually tell us a lot about the deep interior of the moon. Okay. So there's one other possible way to get at this, and this actually is an attempt to try to understand more about how planet formation works. So what are the constraints that we have on the impactor that actually hit the moon? Okay, so we have the moon today is a remnant from that impact, but what can it actually tell us about the source impactor? And to understand that, we have to understand more about how planet formation works in our solar system, and there's different ways it could go. And so I'm going to give you sort of two end-member models to think about. One possibility is that imagine the fundamental planetary accretion is sort of a quiet, gentle process, right? So you can imagine concentric rings going out from the sun, and every ring has its own special reservoir of properties in terms of making different isotopes than the rest. So this would explain why Mars is different from the Earth, but it suggests that if you got an impactor from some other place, it would have a distinct relationship compared to the Earth. So that would suggest then we need equilibration models and other things to explain things. Okay? There's another possibility, which is where perhaps there was lots of radial mixing in the inner solar system. It was a much more violent experience. In that case, you could imagine situations where there's been so much mixing that perhaps the impactor that hits the Earth has very similar properties or very different properties depending on where the impactor comes from. There's a whole range of variety in those different models. And to some degree, the amount of mixing we may have in the inner solar system may depend, strangely enough, on what was happening in the outer solar system. Okay? So today we know from the orbits of Pluto and the Kuiper Belt objects that planet migration had to take place. Neptune had to migrate outward and affect those objects because we see how all those populations have been affected by Neptune resonances. And in fact, this has now become sort of a broad framework for understanding how giant planet migration may have taken place altogether. So what I'm going to show down here in this model is you're looking at a system where the giant planets formed in a different configuration. Jupiter is close to where it is today, but then you have Saturn, Uranus, and Neptune all formed on circular orbits at about half their distance they are right now. Beyond that, we have this large disk of about 20 Earth masses made out of cometary material. And so can someone start the movie? They have to press the bottom there. Thank you. Okay, the color gets weird, I'm sorry. Okay. So what you're looking at here is this system is stable for some period of time. And in this particular simulation, it's stable for hundreds of millions of years. But eventually goes through an instability. That instability causes the migration of the planets out to where we see today. It scatters the disk. But at this point, okay, and so this does all sorts of interesting things throughout the solar system. It explains issues in the asteroid belt, explains all sorts of constraints we have in the outer solar system. But at this point, the planets have already taken, our terrestrial planets and the moon have already taken on their final properties. So this event does not influence the nature of our moon. But it would suggest that we should have an uptick in impacts on the moon and other worlds whenever this instability took place. So it actually sets some very powerful constraints if we can understand the bombardment history. Okay, can I have the next movie, please? Oops, I have to forward it. I'm sorry. There we go. Okay, so in this but recently there's been a new paper that's very provocative that's getting us all excited. And this is the suggestion that maybe the instability did not happen hundreds of millions of years later, but actually the instability may have happened during planet formation. So I'm going to show you a very similar simulation to what you just saw, except now you're looking at semi-major axis and eccentricity. The giant planets are here, the primordial disk is here, but now you're going to see what happens during terrestrial planet formation when the simulation takes place. Can we run the movie, please? Okay, so you see planet formation taking place here, and everything's sort of calm, but then watch what happens after the instability takes place. That should happen here in just a second. Okay, so what happens is you've added this extra source of excitation into the inner solar system. It causes many more things to collide together. You have much more radial mixing between the components in some fashion. And in the end, what you get for a system is not something crazy, but you actually get something that has about the right mass for the mass of Mars, it's got about the right mass for Mercury. Earth and Venus are pretty good, and it's a very viable solution to possibly solving our planet formation problems. But this would say, though, that the properties of the impactor that hit the Earth and the nature of when the moon-forming event took place and all these things is driven by when this instability took place during planet formation, which is a really profound idea and something we're going to explore. And we'll be talking about this more, I'll say, in the focus group today, later at noon. And so with that, all this exciting work, I'm going to hand things off to David Kring, who will tell us more about what happens to the moon after it formed.
Okay, I'm going to be speaking to you about the important role that samples have had in the development of our ideas up to this point and the importance that samples are going to have as we press forward. And one of the ways that I'm going to do that is to use the papers that have been published in the journal Science. For those of you who publish regularly in Science, you know that this journal is the place where some of the most influential papers in this country are published. And I did a survey of the number of papers based on Apollo samples that have been published in that journal thus far, and there have been 124 published in that journal thus far, demonstrating that lunar samples returned to Earth have generated an enormous wealth of transformative scientific knowledge, that goal that we are trying to address today. So I want to walk you through some of the big ideas that have emerged from those analyses. Some of these you've actually heard in other contexts by the previous speakers. One of the big ideas is that the origin of the Earth and the Moon was produced by a giant impact event, and that was based in part on the chemical analyses of the samples returned to Earth, as you heard described. We also, immediately after the Apollo 11 samples were returned to Earth, conceived this idea, John Wood and J.V. Smith and their groups conceived this idea of a lunar magma ocean surrounding the early moon, that the moon, in fact, was a differentiated body. For those of you who don't recall, before those samples were collected, there was a great debate in the community. Was the moon, in fact, a simple, primitive, chondritic body? That was the idea that was championed by Nobel laureate Harold Urey. But in fact, once those samples came back, it was immediately obvious that the moon, in fact, was a differentiated body, and that the highlands seemed to be produced by the flotation of the North acidic rocks that had floated on the top of that magma ocean. Many of the samples that came back also had impact ages around 3.9 and 4 billion years ago. That gave rise to the lunar impact cataclysm hypothesis, which we now refer to as the inner solar system impact cataclysm hypothesis. As for some of the reasons that Bill Bakke just outlined, the data here indicate that the bombardment that we witness on the moon actually affected all of the inner solar system terrestrial planets and was being driven by a reorganization of the outer solar system giant planets. And so if you want a tagline, wandering worlds resurface worlds. We've also realized that some of the largest of those impact events would have vaporized the seas on the Earth. And so for periods of time, life would have been completely untenable at the surface. At the same time, we now recognize that those big impact events generated vast subsurface hydrothermal systems. Those vast subsurface hydrothermal systems would have been perfect crucibles for the prebiotic chemistry and the early evolution of life on our planet, or Mars. And in fact, our good friends in the astrobiological community, looking at the tree of life, have identified that some of the common ancestor community seems to represent thermophilic or hypothermophilic microbial communities, which is those organisms that would thrive very well in one of these impact-generated hydrothermal systems. We also have a couple of emerging hypotheses, that is, hypotheses that have arisen in the last few years. One is the idea of a lunar magmatic epoch hypothesis. Recent analyses of zircon in Apollo samples has indicated that there's a huge number of ages at about 4.35 billion years ago, and it's been hypothesized that that magmatic epoch on the near side was prompted by a very large impact, the South Pole Aitken Basin impact on the far side. And also, as Carly Pieters outlined, we've been drawn to the moon to better understand the origin of lunar and Earth's water, and at least thus far, the delivery seems to be dominated by asteroids and not comets. And all of those big ideas, those transformative scientific ideas, have emerged from the samples curated at the Johnson Space Center. Okay. So I'm going to just pull on one of these ideas, and that is this lunar cataclysm hypothesis, and walk you through that. I've plotted here on the right a diagram which on the y-axis indicates the flux of impacting asteroids and comets as a function of time from 4.5 billion years ago to today. As I mentioned earlier, many of the early analyses indicated a preponderance of ages about 3.9 to 4 billion years ago, and so the idea arose that there was some type of spike in the impact rate. So we had a very high collisional period immediately after the Earth-Moon formation giant impact event. There was some type of decline, and then this large increase at 3.9 to 4 billion years ago. That said, the magnitude and duration of that is still unknown, and so you see I've indicated that with a family of lines, I think 4 different lines there, and if you were to ask me today what I think the correct curve is, it would be the second one from the top, but we'll see if that actually is the case once we go back to the moon and collect appropriate samples to test that idea. Now, for the astrobiologist in the community, this has been very interesting because the cessation of the basin forming event on the moon seems to coincide with the earliest isotopic evidence of life on our Earth. And so there has been this question, is there a cause or effect? And that, of course, lent weight to the impact origin of life hypothesis. Okay, putting all that together, our good friends at the Goddard Space Flight Center have put together this little video that shows some of these processes. And you'll see that there are a couple of ages. I don't hear the music. Have put some ages on that, and that's based on the analyses that we have thus far. But again, we need to go back to the moon to better determine these ages. That's the South Pole Aitken Basin event, maybe 4.35 billion years ago. And then this is the severe bombardment that may have occurred later. And as I said again, the magnitude and the duration of that bombardment is still uncertain, and it does require us to go to very carefully selected sites on the lunar surface to collect new impact lithologies to better determine the cadence of that bombardment. Okay. Now, it may be lost on many of you that the Earth and the Moon weren't in the have the relationship that they have today. And I'm illustrating that with this diagram. You see the Earth and the Moon at the top. The Moon is about 60 Earth radii from us today. At 3.9 billion years ago, it was about 21 Earth radii. And soon after the giant impact event, it was only about 3.8 Earth radii. And so you can imagine the Moon, this lunar magma ocean body in the sky, with a cross-section about 16 times larger than it is today. So I have to say that because these two objects are in the same part of space, they occupy the same niche, if you will, in the solar system dynamical system, we can use the lunar record to estimate the type of collisional environment the Earth was also seeing. And so based on that, we've estimated that there are 200 impact basins 1,000 kilometers in size and 4 to 5 impact basins greater than 5,000 kilometers in size on the Earth. And that collisional evolution would have eroded the Earth's primitive atmosphere, episodically vaporized its nascent seas, as I said before, and likely affected the origin and early evolution of our life. And so it begs the question, could life have emerged from an impact crater on the Earth? Okay, it's also important to remember that that collisional record on the Moon is actually the clock that we use to determine the sequence of events throughout the solar system. And you know that it's very easy to understand the relative consequences. If you have a very old terrain, it's been susceptible to bombardment for a very long time, and so it has a heavily cratered surface, whereas younger terrains, not having existed for and exposed to bombardment very long, have a less cratered surface. By going to specific lunar terrains and determining the ages of rocks collected in those terrains, and correlating them with crater densities, we can actually establish a calibrated clock. And once that calibrated clock is complete, we can then apply that clock to a variety of other objects throughout the solar system. We have a partially calibrated clock based on the Apollo samples, but much more work needs to be done back on the Moon to refine that clock. Lunar samples have also been very important in understanding the evolution of magmatic worlds. And here I've just posed a series of 6 questions to kind of capture some of the ideas that we're exploring. How long was the magma ocean molten? How fast does a planetary crust form? Do mantles overturn? How long does the core dynamo operate? How long does surface volcanism persist? And how does volcanism affect planetary environments? Carly Pieters already pointed out that we may have had a transient atmosphere on the ancient Moon, and that some of these volcanic events may have been very important sources for the volatiles that we want to recover in the south polar terrains of the Moon today. Okay, so I'm returning to this chart that I showed you at the beginning of this presentation, and I've added a bullet. To produce transformative science in the future, we need additional samples from other lunar surface sites whose locations are guided by those past Apollo missions and the spectacular orbiting data that's accumulated over the past 45 years. And I want to point out that we actually have a good idea what those landing sites look like and where they are located. This is just an example of one of the landing site studies that's been produced over the years. This is a global lunar landing site study that the LPI published a few years ago. It's a 688-page monster if you are interested in finding out where we should be landing. In a prioritized scientific sense, you can find that document online. Okay, So I do want to give you just one example. So for those of you in the engineering community who may not have followed some of the scientific discourse that we've had thus far this morning, I want to draw your attention to the Schrodinger Basin. Based on that 6-year study in the report I showed you on the previous slide, the Schrodinger Basin on the lunar far side within the South Pole Aitken Basin is the highest priority landing site that we've identified. If we were, for example, to sample rocks in the uplifted peak ring, those are rocks that came from depths of 25 kilometers, and with them we could test the lunar magma ocean hypothesis, test the giant impact hypothesis, and tap into the lunar water cycle that Carly Pieters described. If we were to sample some of the volcanic rocks within the peak ring, the Mare basalt lava flow and the pyroclastic vent, we could address the thermal and magmatic evolution of the moon and tap again into the lunar volatile cycle at a completely different depth within the lunar interior. If we collect samples of the Schrodinger impact melt, we can determine the end of the lunar cataclysm and basin-forming epoch on the moon. If we go to the walls of the Schrodinger Basin, we believe we can collect samples of the South Pole Aitken impact melt and therefore determine the age of the oldest basin on the moon and assess early solar system bombardment. And those two objectives alone are the first and second highest priority in an NRC document that guides NASA's exploration strategy. In addition, and it's hidden here in yellow, I see it's not showing up very well, that all of the sampling that I've addressed in the Schrodinger Basin, will help address a majority of the science objectives in that NRC 2007 report that the NRC delivered to NASA. Okay, this is just a close-up view to give you a sense of what that sampling site might look like. You could imagine landing a spacecraft between the pyroclastic vent, which we've calculated is the largest indigenous source of volatiles in the South Polar region, and that peak ring, which uplifted rocks from the lunar interior from depths of 20 to 30 kilometers. There is both scientific potential at this site, and there's extraordinary ISRU potential too, in part because of the volatiles that were erupted, in part because the pyroclastic material is very useful building material, and also because the pyroclastic material in a nearby Mare deposit can be fluxed with hydrogen to actually precipitate water using hydrogen reduction processes. I want to skip over this slide because as a group we've run a little long and actually migrate to a slightly different, actually a vastly different scientific initiative. I see Jack Burns smiling over here. I focused my comments largely on samples because it was the samples of Apollo that completely changed our understanding of the Earth-Moon system and largely altered our understanding of the entire evolution of the solar system. However, that far side location that I was just speaking to at the Schrodinger Basin within the South Pole Aitken Basin is, after we complete that geologic exploration, is a perfect place to deploy radio telescope antennas, and those radio telescope antennas being shielded from the radio noise from the Earth would be a perfect asset for detecting radiation from some of the earliest events in the universe. And I'm not going to walk you through this diagram in great detail, but I do refer you to Jack Burns from the University of Colorado, one of the other survey PIs, for details if this type of science intrigues you. Okay. I have two more slides, and this really gets to the implementation of the program that we've been outlining. I think the first thing that's important for everybody to recognize, because it has, I think, been overlooked, in part because we've not had a human exploration program on a planetary surface for 45 years, but I think it's very important that we all understand that the best results will be obtained by a well-trained crew on the lunar surface. And while that capability is being developed, significant progress can be made robotically with an integrated robotic human and architecture, such as deploying crew to the Earth-Moon L2 location above the lunar far side in Orion or an orbiting platform such as Gateway. Robotic assets we've also determined, such as the Lunar Electric Rover, can perform additional science and exploration tasks between human missions to the surface. And for those of you who are not familiar with the Lunar Electric Rover, this is an incredibly capable vehicle that was built at the Johnson Space Center. I want to leave you then with 5 simple messages, and again, this goes to the implementation. I would argue that we need to explore the unexplored. That means we go to the lunar far side and the poles. I would argue that leadership begins with meaningful missions. It's very easy to do simple, inconsequential measurements, but I think that we need to get past that and land on the lunar surface. To make truly transformative scientific discoveries, I hope the examples that I've shown you today indicate the need for sample return missions to high-priority landing sites. It goes without saying that an integrated robotic and human exploration program with international and commercial partners will produce the greatest science, and I look forward to that. And I hope that we don't forget our customers. As a scientific community and an engineering community, we need to engage the public and Congress. We need, for example, to provide a communication relay to the far side with a high data rate and the capability, again, for example, of providing them with HD video of our exploration efforts. With that, thank you, and give it back over to Yvonne.
Okay, that was great, and that was just as good this time as when we did it at headquarters. So this is time for you to ask the panel questions, and we have microphones here and here. We may also have a roving mic, but I think, yes, why don't you bring the roving mic down, Ashkan? So we have nobody at the mic yet. Jack has a question. Can you get up and ask from there, please? So that the recording can capture what you're saying.
Sure. Jack Burns, University of Colorado. So what we're hearing from some folks at headquarters is there are not current plans to go to the poles and the far side. And I don't understand that. And I think that message, David, that you were just delivering, I like the way you framed it here, explore the unexplored, means almost by definition of that those 2 sites are where we need to go. So we have some work to do to convince folks that these are the prime targets for both human and robotic exploration in moving forward. They may not be the safest place, they may be more difficult to get to, but scientifically and from an exploration perspective, I think you all made the case that that's where we need to go.
I can maybe just illustrate that point with one more data point. We've put 37 missions on the near side and none on the far side. We've hit a polar region, but we've not landed there. So yes, that's where we need to go.
Let me comment on
Okay.
that, too.
We can come
Everything
back.
David said is correct. However, there's a heck of a lot of areas, even on the near side, that we haven't visited and they're still unexplored. The swirls, a suite of pyroclastic deposits, the youngest basalts. The landing site forum that was here earlier this year identified a whole suite, and I believe that will be presented sometime this morning. So although the poles in the far side clearly are very high priority because they are completely unexplored, that's not to say there are other areas on the moon that don't merit exploration as well.
So, yeah, but let me pull at that one a little bit, Carly. I absolutely agree. The global exploration, global landing site study that we produced literally identified every site that we thought we could land and help address some of the NRC 2007 objectives. So there is a plethora of landing sites on the near side as well. But when one is designing complex engineering systems, a complex architecture, you want to make sure that you don't do something that restricts global access to the moon. And if there are hardware elements that are required to do the things that are hard, you need to know about them sooner rather than later. And so that's why I think we really need to have an understanding that the polar regions and the far side have to be on our list of important targets to go to.
Okay, thank you. We have another question at the microphone. Those of you in the back with questions, please come and line up at the microphone. Okay, Lika.
This was a fascinating crash course for me, so I want to thank the panel. Haven't thought about science from the moon in a while. One of the things I didn't see here, and I think there is great potential, especially given, the climatic changes that we are experiencing on our own planet, and this is really getting a pristine core from the moon to really understand sort of the impact of sun on climate through solar energetic particles and various things like that. We've tried to do that on Earth through ice core, and there's contamination, volcanoes, all of that. I think that would be really awesome. Just wanted to hear your thoughts on that.
You want Dan to say it? I can if you, but it's really your area.
First of all, thank you for that comment. You're absolutely correct. The report that we prepared, as you can see, is a very short report. And we didn't spend a lot of time on all the important questions, and the dust and the exosphere. The current environment of the moon clearly has a lot of discussion that needs to be continued, whether it's another separate white paper, but clearly that topic is of great importance for the very reasons that you outlined. And I urge the community to be thinking of that. That's exactly the sort of thing that we want this forum to be stimulating.
Great. We'll take one more question.
Suman Badagere Ramaya from University of Southern California. That was a very interesting talk. From the exploration perspective, definitely the poles and the far side are more intriguing. But from the settlement perspective, for the long-term settlement perspective, we need a lot of things like construction material, the communication, like in the near side you have constant communication to Earth. And the studies have found that 26% of the near side moon is basalt, whereas only 2% on the far side of the moon. So, and also recently they have found mogonite in the near side of the moon. The meteorite that was fallen on the African continent, they studied and they found the mogonite that came from moon was from the near side of the moon. So from the construction perspective, the pyroplastic materials that you were talking, near side has a lot of resources like that. So if you stop by at my poster later, I will be talking more about that. So, but I want your perspective of like in the long-term settlement perspective, considering near side is also equally important as we consider from the exploration perspective on the far side.
I can take that. All right. So first of all, I want to applaud and welcome your enthusiasm for exploring the moon and settlement of the moon. That's even more exciting. Yeah, so I would have to say that at the moment, our understanding of resource potential is still immature on the moon. It is absolutely true that via hydrogen reduction, we can produce water from the Mare sites, of which there are more on the near side than on the far side. But we're also been looking at the potential of ice-rich deposits in the polar regions. And if those deposits are in fact there, that actually may be a far more important resource. And so we need to do a little bit of prospecting to see exactly how real those deposits are. Now, you did point out that there is an advantage to being on the near side because of direct line of sight communications. And that certainly was important during Apollo when we didn't want to stretch risks. I know Jack really wanted to go to the far side and he wasn't allowed to. But we know how to relay communications at very high bandwidths. I pointed this out, I think it was last year, that we have 2,000 comm satellites in Earth orbit. If we put up 1, 2, 3, or 4 around the moon, we can talk to the far side as confidently as we can with the near side. So I don't think near side comm really should be a driver.
But let me add one thing that could make the near side interesting, and it could also the far side. But one thing we haven't discussed are this new potential for caves. Like actually going into a cave, getting radiation protection, having a natural shelter could be a very powerful driver for settlement, and maybe that has advantages that outweigh other things. And that's something that will have to be evaluated as we understand caves on the moon more.
Yeah, well, but I think, again, we have evaluated that. I don't really understand the popularity of this concept. If you've ever gone through a skylight into a lava tube, it's scary. And it's not something you want to do in a spacesuit. Moreover, we actually have designed systems like the Lunar Electric Rover that JSC built that can mobilize regolith and pyroclastic debris and produce shielding equivalent to that of a lava tube roof. So I would suggest the settlement, if it's going to be driven by radiation protection, shouldn't be limited to caves.
Okay, Carly gets the last word on this, and then we're going to shut this down.
Well, I think this discussion, short as it is, I hope has stimulated a lot of thought that will continue through the week. Clearly, and we'll hear from headquarters people in a moment, this is a program. This is not a single mission. And a program must have many elements and must have a long-term plan. So we don't have to worry if we go here, we can't go there. We need to be thinking of global, important, transformative science.
That's very good. Thanks for ending it that way. Thanks for the entire presentation. Let's give them a big round of applause.